Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the astonishing world of atomic physics and discovering the laws of nature at its smallest scale. This humble science has given us extreme power, and it has changed how we understand the very fabric of reality itself. An atom may seem simple at first, yet inside it, nature behaves in ways that are deeply surprising. This hidden world is not distant from daily life. It shapes color, it keeps time, and it supports the technology we use every day. Atomic physics is also a story of discovery. It began with a simple question about matter, but it led scientists into a realm where certainty disappears, and the ordinary world reveals a stranger set of rules. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Allow your shoulders to soften. Allow your eyes to grow heavy. And as the day begins to gently fade away, join me as we explore this fascinating world together. Let's begin. Atoms are mostly empty space, yet they build everything that is solid. This sounds impossible at first, because a table feels firm, a stone feels heavy, and your hand cannot pass through a wall. But inside every atom, the nucleus is tiny compared with the space around it. If the nucleus were enlarged to the size of a small pea, the outer edge of the atom would be far across a building. The strange part is that solidity does not come from atoms being packed like little beads. It comes from forces. Electrons spread around nuclei in quantum patterns, and those patterns strongly resist being pushed into the same state as other electrons. When your fingers touch a surface, the atoms in your skin never truly merge with the atoms in the object. Their electron clouds repel and rearrange. That resistance is what your nerves report as touch. So the solid world is not solid in the simple way we imagine. It is a beautifully organized standoff between invisible fields. Atomic physics gave humanity the clockwork behind modern technology. The hidden behavior of atoms may seem far removed from daily life, but it quietly supports much of the modern world. Once scientists learned how electrons absorb energy, emit light, and arrange themselves around nuclei, they gained the foundations for a new kind of engineering. Transistors depend on quantum behavior in materials, and transistors became the heart of computers. Lasers rely on controlled atomic emission, and lasers now scan groceries, send information through fiber optic cables, and guide delicate surgery. Atomic clocks keep time so accurately that navigation systems can calculate position across the globe. Magnetic resonance imaging depends on the response of atomic nuclei inside the body. None of these inventions began as ordinary mechanical improvements. They grew from asking how matter behaves when examined closely. Atomic physics turned invisible rules into practical tools. It gave civilization a clockwork that is not made of gears, but of energy levels, fields, and light. Every color in a flame reveals a hidden atomic signature. When a flame changes color, it is not just putting on a show. It is revealing which atoms are present. Heat gives energy to the atoms in a substance, and their electrons move into higher energy states. They cannot remain there for long. When they fall back, they release light of very specific colors. Sodium gives a strong yellow glow. Copper can produce blue-green light. Strontium is often used for red. This is why fireworks can be designed with such precision. Their colors are not painted into the sky. They are released by atoms, obeying exact quantum rules. The same idea allows scientists to identify chemicals in distant stars. A little line of color can act like a fingerprint from matter itself. In a flame test, a tiny sample can announce its identity without words. It is one of the simplest ways atomic physics turns something familiar into something astonishing. Electrons can vanish from one energy level and appear in another. In everyday life, movement usually feels continuous. A ball rolls across the floor. A bird crosses the sky. It passes through the space between where it began and where it ends. But electrons inside atoms do not change energy in that smooth, familiar way. They occupy allowed energy states, and when they shift, they do so in sudden steps. The electron is not like a tiny marble climbing a staircase. It is described by a quantum state, and that state changes when the atom absorbs or releases the right amount of energy. This is why atomic spectra have sharp lines rather than blurred bands. Each line marks a precise jump. The idea was so strange that it helped break classical physics apart and open the door to quantum theory. A tiny electron forced scientists to accept that nature, at its deepest measurable levels, does not always move by the rules our senses expect. A single atom can be trapped, cooled, and studied almost motionless. For most of human history, atoms were far too small and restless to handle directly. They were ideas, then measurements, then patterns inferred from experiments. Today, scientists can isolate a single atom and hold it in place using electric fields, magnetic fields, or carefully arranged light. In some experiments, atoms are cooled to temperatures far below anything found in ordinary life. Cooling does not mean making them frosty in the familiar sense. It means slowing their motion until their quantum behavior becomes easier to observe. The trapped atom can be watched as it absorbs light, emits photons, or changes state. It becomes a laboratory almost by itself. The achievement is breathtaking because an atom is not a miniature object with convenient handles. It is a delicate system that can be disturbed by tiny outside influences. To hold one steady is to make nature pause long enough for us to study one of its smallest working parts. Light itself taught scientists that atoms obey strange quantum rules. The path to atomic physics did not begin with seeing atoms directly. It began with light behaving in ways that ordinary physics could not explain. Heated objects glowed with patterns that puzzled scientists. Certain gases emitted sharp colors instead of a continuous rainbow. The photoelectric effect showed that light could knock electrons from metal only when its color carried enough energy. Brighter light did not solve the problem if the color was wrong. These clues suggested that light arrived in packets, later called photons. Once that idea took hold, atoms began to look different too. Their electrons could not have just any energy. They responded to light in exact portions. The study of brightness, color, and emission lines became a doorway into a deeper world. Light was not merely illuminating matter. It was carrying messages from matter's hidden structure, and those messages revealed that nature keeps accounts in tiny, indivisible exchanges of energy. The same atoms in your body once drifted through ancient stars. The atoms that make up living things have a history far older than life on Earth. Hydrogen formed early in the universe, while many heavier elements were forged later inside stars or created during powerful stellar explosions. Carbon, oxygen, calcium, and iron did not simply appear on our planet. They were assembled through nuclear processes across cosmic time, then scattered into space, where they became part of new clouds, new stars, and eventually new worlds. When you breathe, move, or think, you are using matter that has already passed through vast chapters of cosmic history. This does not mean your body is metaphorically connected to the stars. It means the connection is physical. The atoms are real. Their origins can be traced through astrophysics and nuclear physics. Atomic physics helps explain how these elements behave once they exist. In that sense, the human body is not separate from the universe's story. It is one of its later arrangements. Atomic clocks measure time by listening to vibrating atoms. A cock needs something regular to count. A pendulum swings. A quartz crystal vibrates. An atomic clock uses something far more stable, the transition of atoms between precise energy states. In a cesium clock, atoms are exposed to microwaves tuned to a specific frequency. When the frequency is exactly right, the atoms respond by changing state. The clock adjusts itself to stay locked to that response. This is not timekeeping by machinery alone. It is timekeeping by a property of nature. The modern definition of the second is based on a particular cesium transition, counted through billions of cycles. Such accuracy matters because tiny timing errors become large position errors in navigation. They also affect communication networks, scientific measurements, and tests of fundamental physics. Atomic clocks are not just better watches. They are instruments that reveal time as something measured through matter's most reliable rhythms, repeating with a steadiness no human mechanism can match. Lasers work because atoms can release light in perfect step. Ordinary light is often mixed and disorderly. Its waves may have many colors, directions, and timings. Laser light is different because its photons can be made to match one another. The key idea is stimulated emission. When an excited atom is encouraged by a passing photon of the right energy, it can release another photon that matches the first. The new photon has the same color, direction, and phase. If this process happens again and again inside a carefully designed material, light becomes organized into a narrow, powerful beam. This is why lasers can cut metal, read disks, scan barcodes, and carry internet data through glass fibers. Their usefulness comes from atomic precision. The beam may look smooth and continuous, but it is built from countless tiny emissions made orderly by quantum rules. A laser is one of the clearest examples of how a strange atomic process became a tool of everyday civilization. The universe became transparent when the first atoms finally formed. In its earliest stages, the universe was so hot that electrons could not settle around nuclei. Matter existed as a charged plasma, and light could not travel freely because it kept scattering from loose electrons. The universe was filled with radiation, but it was not transparent. As space expanded, the temperature fell. Eventually, electrons joined with nuclei to form neutral atoms, mostly hydrogen and helium. Once those free electrons were removed from the cosmic fog, light could move across vast distances. That ancient light still exists today as the cosmic microwave background. It is not light from stars. It is the afterglow from the time when atoms first allowed the universe to become visible. This moment transformed the cosmos. Before it, light was trapped in a hot, dense haze. After it, radiation could stream outward, carrying a record of early conditions. The birth of atoms helped create the universe we can observe. Ancient Greek thinkers imagined atoms long before anyone could see them. More than 2,000 years ago, some philosophers proposed that matter might be made of tiny, indivisible pieces. Leucippus and Democritus argued that if you kept cutting a substance into smaller parts, you would eventually reach something that could not be cut further. They called these imagined pieces atoms, from a Greek word meaning uncuttable. Their idea was not based on modern experiments. It was a bold attempt to solve a problem using reason. For centuries, the concept remained philosophical rather than scientific. Many thinkers preferred the idea that matter was continuous or built from classical elements. Yet the ancient atomists planted a question that refused to disappear. What is matter made of at its deepest level? When later scientists measured gases, chemical reactions, and electrical behavior, the old idea returned in a transformed form. The Greek atom was not the atom we know today, but it was the first clear step toward imagining a hidden structure beneath ordinary objects. John Dalton turned the old idea of atoms into science. At the beginning of the 19th century, chemistry was filled with careful measurements that needed a clear explanation. Substances combined in fixed proportions. The same compound always contained the same relative amounts of its ingredients. John Dalton saw that these patterns made sense if each element consisted of its own kind of atom, and chemical reactions rearranged those atoms without creating or destroying them. His model was simple compared with modern atomic theory, but it gave chemistry a powerful foundation. Water, carbon dioxide, and countless other compounds could be understood as combinations of definite particles. Dalton also introduced atomic weights, which allowed scientists to compare elements in a more systematic way. He was not able to see atoms, and he did not know about electrons, nuclei, or isotopes. Even so, his work moved atoms out of philosophy and into testable science. The invisible building blocks became part of a measured, predictive description of matter. J.J. Thomson discovered electrons using glowing beams in glass tubes. In the late 19th century, strange rays appeared inside sealed glass tubes when high voltage was applied. These cathode rays seemed to travel from one metal plate toward another, creating a glow on the glass. J.J. Thomson studied how the rays bent in electric and magnetic fields. Their behavior showed that they were made of tiny negatively charged particles, much smaller than atoms. This was a stunning discovery. Atoms had often been treated as indivisible units, but Thomson showed that they contained smaller parts. The electron had entered science. His work changed the picture of matter almost overnight. If atoms had internal pieces, then atomic structure had to be explained. Thomson proposed an early model with electrons embedded in a spread of positive charge. That model would later be replaced, but the discovery itself endured. A glowing tube revealed that the atom was not the end of the story. It was a doorway into a deeper level. Rutherford found the atomic nucleus by firing particles at gold foil. Ernest Rutherford and his colleagues performed one of the most famous experiments in physics. They aimed positively charged alpha particles at an extremely thin sheet of gold. Most passed through with little change, which suggested that atoms were not solid balls. A small number, however, bounced back at large angles. Rutherford compared the surprise to firing a shell at tissue paper and having it rebound. The result meant that an atom's positive charge and most of its mass were concentrated in a tiny central nucleus. The rest of the atom was largely open space. This overturned Thomson's earlier model and gave scientists a new target for understanding matter. The nucleus was incredibly small, yet it dominated the atom's mass. That discovery opened the path toward nuclear physics, radioactivity studies, and a new understanding of elements. A thin sheet of gold had revealed that the heart of the atom was compact, powerful, and unexpectedly dense. Bohr pictured electrons circling atoms in fixed energy levels. Niels Bohr wanted to explain why hydrogen produced sharp spectral lines instead of every possible color. He proposed that electrons could occupy only certain allowed orbits around the nucleus. When an electron moved between these levels, it absorbed or emitted light with a precise energy. This model was not the final truth, but it explained hydrogen better than earlier ideas and gave physicists a bold new picture. It suggested that atomic stability depended on rules unlike anything in classical mechanics. Electrons were not simply falling into the nucleus, even though ordinary electromagnetism seemed to predict that they should. They were restricted to specific states. Bohr's model also connected atomic structure with observable light, turning spectral lines into evidence of hidden energy steps. Later, quantum mechanics replaced the orbit picture with wave functions and orbitals. But Bohr's insight remains a crucial turning point. He made the atom feel like a system with secret rungs on an invisible ladder. Quantum mechanics replaced tiny orbits with clouds of probability. The neat image of electrons circling like planets was useful, but it could not survive the full evidence. Experiments showed that electrons did not behave like little objects following definite paths around a nucleus. Instead, quantum mechanics described them with wave functions. These wave functions do not show where an electron is in the everyday sense. They give the probability of finding it in different regions if a measurement is made. This led to atomic orbitals, shaped zones of likelihood rather than physical tracks. Some are spherical. Others have lobes and nodes where the electron is unlikely to be detected. The change was difficult to accept because it challenged the ordinary idea of motion. An electron in an atom is not simply hiding somewhere until we look. Its state is described by a spread of possibilities. This probability picture became one of science's most successful tools, explaining chemical bonds, spectra, magnetism, and the structure of the periodic table. An electron behaves like a particle and a wave at once. The electron is one of the clearest signs that nature does not fit neatly into everyday categories. In some experiments, it behaves like a tiny particle. It arrives at a detector in a single localized event. In other experiments, it produces interference patterns, which are the signature of waves. The famous double-slit experiment shows this beautifully. Even when electrons are sent one at a time, the final pattern builds up, as if each electron has passed through a wave of possibilities. This does not mean the electron is switching costumes in a simple way. It means our familiar words are incomplete. Quantum objects have properties that can appear particle-like or wave-like, depending on how we measure them. This discovery shook physics because it showed that matter itself has wave behavior. The same principle is now used in electron microscopes, which can reveal structures far smaller than ordinary light microscopes can resolve. The electron's strangeness became a powerful tool. No microscope can show an electron like a tiny planet. It is tempting to imagine that a better instrument could one day reveal an electron as a small sphere racing around the nucleus. Atomic physics says otherwise. An electron is not known as a tiny planet with a visible surface. It is an elementary particle, and within current experiments, it has no measured internal size. When bound in an atom, it is described by a quantum state rather than a path that can be photographed. Microscopes can image atoms in indirect ways, and particle detectors can record electron interactions. But none of this produces a simple portrait of an electron sitting in space. The limits are not just technical. They arise from the nature of quantum measurement. Trying to locate an electron more sharply changes what can be known about its motion. This is why textbook drawings are useful only as symbols. The real electron is stranger than any little orbiting world, and more precise than any picture can capture. Atomic orbitals describe where electrons are most likely to appear. Orbitals are among the most important ideas in atomic physics because they connect the invisible quantum world to the behavior of matter we can touch. An orbital is not a path. It is a mathematical description of an electron's allowed state inside an atom. From it, scientists calculate regions where the electron is likely to be found. These regions have shapes, and those shapes help determine how atoms bond. The simplest orbital around hydrogen is round, with the electron equally likely in every direction around the nucleus. Other orbitals have more complicated forms, with directional lobes that influence the geometry of molecules. This is why water has a bent shape, and why carbon can build such varied structures. Orbitals also explain the organization of electron shells and the repeating patterns in the periodic table. They turn probability into architecture. The shapes are not solid containers, but they guide the chemistry that builds minerals, air, living cells, and technology. The simplest atom in the universe is plain hydrogen. Hydrogen usually contains one proton and one electron. That tiny pairing makes it the lightest and most basic atom. Its simplicity is one reason it became central to atomic physics. Scientists could study its light in great detail and compare observations with theory. Because it has only one electron, hydrogen allowed physicists to test ideas that would be much harder to untangle in heavier atoms. Its spectral lines helped reveal energy levels, and its structure became a testing ground for quantum mechanics. Yet this simple atom is not merely a laboratory convenience. It is also the most abundant element in the universe. Great clouds of hydrogen help form stars, and inside stellar cores, hydrogen nuclei provide fuel for fusion. On Earth, hydrogen appears in water, organic molecules, and many industrial processes. It is modest in structure, but enormous in importance. The smallest complete atom has shaped both the history of physics and the history of the cosmos. Hydrogen atoms still fill most of the visible universe. After the universe cooled enough for matter to take stable form, one element became the great majority of ordinary material. It was hydrogen. Even today, after billions of years of stars burning, exploding, and enriching space with heavier elements, hydrogen remains the dominant ingredient in the visible cosmos. It drifts between galaxies, gathers in vast clouds, and collects under gravity until new stars can begin. In many ways, every glowing star is a story about hydrogen being squeezed, heated, and transformed. Our own sun still depends on it at the core, where nuclei fuse and release the energy that reaches Earth as daylight. This small atom is also a reminder that complexity can grow from simplicity. From one proton and one electron came the raw material for stellar birth, galactic structure, and future chemistry. The universe may look full of different things, but its visible matter is still largely shaped by the simplest atom ever made. Helium was discovered in sunlight before it was found on Earth. During a solar eclipse in the 19th century, scientists studied the colored lines in light from the sun's atmosphere. Among those lines was one that did not match any known element on Earth. It appeared as a bright yellow signal, close to sodium, but not quite the same. Instead of assuming it was a mistake, researchers proposed that the sun contained an unknown substance. They named it helium, after Helios, the Greek sun god. Years later, the same element was identified in minerals on Earth, confirming that sunlight had revealed it first. That sequence is astonishing because it shows how atomic physics can discover matter at a distance. No sample had been brought from the sun. No spacecraft had visited it. The evidence came from light alone. A color in the solar spectrum was enough to announce a new element, turning the sun into a laboratory across space and proving that atoms could speak through their spectral lines. Every element has its own pattern of atomic fingerprints. When atoms absorb or emit light, they do not choose colors at random. Their electrons can move only between specific energy states, and each element has its own arrangement of those states. The result is a unique pattern of spectral lines. Scientists often compare this to a fingerprint because it can identify a substance even in a mixture. Hydrogen has one pattern. Iron has another. Mercury, calcium, and lithium each display their own. This is why a glowing gas can reveal its identity without being touched. It is also why astronomers can analyze material that is impossibly far away. When starlight is spread into its spectrum, dark and bright lines show which atoms were involved. The same principle works in laboratories, factories, and forensic investigations. Each element carries a hidden code in the way it handles light. Atomic physics teaches us to read that code, and suddenly matter begins to identify itself. Spectroscopy lets scientists read atoms from light across space. A telescope does more than collect a beautiful image. When attached to the right instrument, it can spread incoming light into a detailed spectrum, where tiny lines reveal the presence of particular atoms. This method lets scientists study objects they can never visit. The atmosphere of a star, the gas around a newborn planet, and the material in a distant nebula can all leave marks in light. Some lines appear bright because atoms are emitting energy. Others appear dark because atoms have absorbed certain wavelengths before the light reached us. By measuring these patterns, scientists can learn composition, temperature, motion, and sometimes magnetic activity. The power of the technique is almost hard to believe. A faint beam that has crossed space for many years can arrive at a detector and carry an atomic record inside it. Spectroscopy turns light into evidence. It allows the universe to be examined not by touch, but by careful listening to color. Astronomers identify distant stars by decoding their atomic spectra. A star may look like a point of light, but its spectrum is packed with information. When starlight passes through the outer layers of the star, atoms absorb precise wavelengths. Those missing wavelengths appear as dark lines. By matching them to known atomic patterns measured on Earth, astronomers can tell which elements are present in the stellar atmosphere. This was how scientists learned that stars are not made from mysterious heavenly material. They are built from the same elements found in laboratories, though in very different conditions. Spectral details also reveal whether a star is moving toward us or away from us, because the lines shift slightly with motion. The width of the lines can hint at temperature and pressure. A star too distant to show a surface can still be understood through its light. Atomic physics gives astronomers a kind of chemical hearing, allowing them to recognize stellar matter by the exact notes it removes from the rainbow. Neon signs glow because excited atoms release colorful light. Inside a glass sign, a gas waits under low pressure. When electricity passes through it, electrons in the gas atoms gain energy and move into excited states. They soon drop back down, releasing light. Neon itself gives a strong red-orange glow, which became famous in city signs. Other colors often come from different gases or from coatings inside the tubes. The beauty of the sign comes from the same principle behind much of atomic physics. Atoms emit light in characteristic ways when their electrons change energy. The glass tube only shapes the message. The color is born inside the atoms. This makes a neon sign more than decoration. It is a public display of quantum behavior, hanging above streets and storefronts. Every glowing letter is powered by the exact energy structure of matter. What looks like advertising is also a small lesson in how atoms turn electrical energy into visible light. Sodium lamps shine yellow because sodium atoms prefer that color. For many years, city streets and tunnels were lit by lamps that gave everything a distinctive golden cast. That color came from sodium vapor. When electric current energized the gas inside the lamp, sodium atoms emitted light very strongly at a pair of closely spaced yellow wavelengths. Human eyes perceive this as an intense yellow glow. These lamps were efficient, which made them useful for public lighting, but they also made colors hard to distinguish because most of their light was concentrated in a narrow part of the spectrum. The effect could make cars, buildings, and faces seem flattened into one warm shade. The reason was not aesthetic choice. It was atomic structure. Sodium's electrons release energy in a way that favors yellow light. A whole city could take on a particular nighttime appearance because of one element's internal rules. That is the strange reach of atomic physics, from a microscopic transition to the mood of an illuminated street. The green glow of auroras comes from excited oxygen atoms. High above Earth, charged particles from space can pour into the upper atmosphere along magnetic field lines. They collide with atoms and molecules, transferring energy in the thin air. Oxygen atoms can hold that energy for a brief time before releasing it as light. One important emission appears green, and it is responsible for the most familiar auroral glow. This light is produced at altitudes where the air is sparse enough for excited oxygen to survive long enough to emit its photon before another collision interrupts it. Lower down, the air is denser, and the process changes. The result is a sky that can shimmer in sheets, arcs, and rippling curtains. The display may feel mysterious, but it is made from atomic events happening overhead in enormous numbers. Each flash of green is a tiny release from oxygen. Together, those releases become one of Earth's most unforgettable natural spectacles, written across the polar sky. Atomic energy levels explain why fireworks have such vivid colors. A firework is carefully designed chemistry, but its brilliance depends on atomic physics. When the burst ignites, heat excites atoms and ions inside the exploding mixture. As their electrons return to lower energy states, they emit light of particular colors. Different ingredients are chosen because they favor different wavelengths. Strontium compounds can help produce red. Barium compounds can contribute green. Copper compounds can create blue, though blue is difficult because high temperatures can disrupt the chemistry needed for a clear shade. The timing, shape, and crackle of a firework involve engineering, but the color is controlled by transitions inside matter. That is what makes the display so precise. A sky full of fireworks is not merely burning powder. It is a sequence of atomic announcements, each one created by energy moving through allowed quantum steps. The drama lasts only seconds, yet every color depends on rules that are as exact as anything in a laboratory. Electrons cannot spiral into the nucleus because quantum rules forbid it. Classical physics created a serious puzzle. An electron moving around the positive nucleus should radiate energy, lose speed, and fall inward. If that were true, atoms would collapse almost instantly. Matter as we know it would not exist. The solution came from quantum mechanics. Electrons in atoms occupy allowed states, and the lowest of these states has a fixed energy. There is no smaller orbit for the electron to sink into in the old mechanical sense. The electron is described by a wave function spread around the nucleus, not by a charged bead circling on a track. Its stability comes from the rules that govern possible states and from the uncertainty built into quantum behavior. This is not a small detail. It explains why atoms can endure, why chemistry can happen, and why matter has reliable structure. The fact that your body does not collapse into nuclear dust is one of quantum theory's everyday miracles. The Pauli exclusion principle helps give matter its structure. One of the most important rules in physics says that certain particles cannot share the same complete quantum state. Electrons belong to this family of particles. Inside atoms, this rule forces electrons to spread into different states rather than all dropping into the lowest one. Because of it, atoms develop shells and subshells. Those shells shape chemical behavior, material strength, and the order of the periodic table. The same principle also helps explain why ordinary objects resist compression. When electron states are already occupied, other electrons cannot simply pile into them. This creates a powerful form of resistance at microscopic scales. The rule is not a force in the familiar sense, but its effects are everywhere. It helps make matter spacious, structured, and varied. Without it, the universe would lose much of its richness. The difference between elements, the hardness of materials, and the architecture of chemistry all depend on this silent quantum restriction. Chemistry exists because electrons arrange themselves in orderly shells. The reason atoms combine in predictable ways lies mostly in their electrons. These particles occupy energy levels that form patterns around the nucleus. The outermost electrons are especially important because they are the ones most involved in bonding. Some atoms tend to give them up. Some tend to gain them. Others share them, creating molecules with stable arrangements. This is why oxygen, carbon, sodium, chlorine, and every other element behaves with its own recognizable style. The shells do not merely decorate the atom. They decide how the atom meets the rest of the world. Table salt forms because sodium and chlorine can reach more stable electron arrangements by transferring charge. Water forms because atoms share electrons in a shape that gives the molecule unusual properties. Organic chemistry becomes possible because carbon can make several strong bonds. Behind every scent, flavor, mineral, and living cell is the same hidden pattern. Electrons seeking allowed arrangements that matter can sustain. The periodic table is really a map of atomic structure. At first glance, the table of elements looks like a chart of names and symbols. Its deeper power comes from the way it organizes atoms by internal design. Elements are arranged by atomic number, which counts protons in the nucleus. As that number rises, electrons fill available states in patterns. Those patterns cause similar chemical behaviors to repeat in columns. That is why lithium, sodium, and potassium share certain traits, even though their atoms are different sizes. It is also why noble gases gather together as unusually unreactive elements. The table is not just a memorization tool. It is a portrait of quantum order. Its shape reflects electron shells, subshells, and the repeating consequences of atomic structure. Before all elements were known, gaps in the table helped scientists predict missing ones. That predictive success showed that the chart had captured something real. It is one of science's most elegant designs because it makes the invisible architecture of atoms visible. Noble gases rarely react because their electron shells are filled. Helium, neon, argon, krypton, xenon, and radon are known for their reluctance to form ordinary chemical bonds. The reason lies in their outer electron arrangements. These atoms already have stable filled shells, so they have little tendency to gain, lose, or share electrons. For a long time, scientists considered them almost completely inert. Even their name suggests a kind of chemical aloofness. Later discoveries showed that heavier noble gases can form compounds under special conditions, especially xenon, but their general behavior remained striking. Their stability makes them useful in lighting, welding environments, and scientific instruments where unwanted reactions would be a problem. Helium fills balloons because it is light and does not burn. Argon protects hot metals from reacting with air. Neon produces a famous glow when energized. These elements show how a simple electronic arrangement can shape practical use. A filled shell can make an atom seem almost serene in a world of restless chemical exchange. Alkali metals react fiercely because one electron is loosely held. Lithium, sodium, potassium, rubidium, cesium, and francium set in the first column of the periodic table. Their outer structure gives them one electron beyond a filled shell. That electron is relatively easy to remove, especially in the heavier members of the group. When these metals encounter water, they can transfer that electron rapidly, producing heat and hydrogen gas. Sodium may fizz and dart across the surface. Potassium can ignite with a lilac flame. Cesium reacts with even greater intensity. The violence is not random. It comes from a strong drive toward a more stable electron arrangement and from the energy released during the reaction. These metals are soft enough to cut, bright when freshly exposed, and quick to tarnish in air. Their dramatic behavior makes them memorable, but the real lesson is deeper. One outer electron can decide whether an element sits calmly in a container or bursts into motion at the touch of water. Isotopes are atoms of one element with different nuclear weights. Atoms of the same element always have the same number of protons. That number gives the element its identity. Yet the number of neutrons can vary. These variations are called isotopes. Carbon, for example, always has 6 protons, but different carbon atoms can carry different numbers of neutrons. This changes the atom's mass without changing its place in the periodic table. Some isotopes are stable. Others are radioactive, which means their nuclei transform over time. Isotopes are powerful tools because they behave almost alike chemically while carrying different nuclear signatures. Scientists use them to trace water through environments, follow nutrients through living systems, study ancient climate, and date archaeological material. Medicine uses selected isotopes for imaging and treatment. The idea is subtle but revolutionary. 2 atoms can be chemically the same element, yet their nuclei can tell very different stories. Isotopes add hidden variety to matter, turning the nucleus into a clock, a label, or a source of energy. Carbon dating works because one carbon isotope quietly decays. Living things constantly exchange carbon with their environment. While alive, they contain a small amount of radioactive carbon-14, which is produced in the atmosphere and enters the food chain. After death, that exchange stops. The carbon-14 already present begins to decay at a known rate. By measuring how much remains in a sample, scientists can estimate when the organism died. This method has transformed archaeology and the study of recent natural history. It can date wood, bone, seeds, cloth, and other once living materials. It does have limits. It works best for remains up to tens of thousands of years old, not for dinosaurs or the oldest rocks. It also requires careful calibration because the amount of carbon-14 in the atmosphere has varied over time. Still, the principle is remarkable. A slow nuclear change inside carbon atoms becomes a clock hidden in ancient material. Something invisible lets researchers place human artifacts and vanished lives into time. Atomic mass comes mostly from the nucleus, not the electrons. An atom may be defined partly by its electrons, but almost all of its mass is concentrated at the center. Protons and neutrons are each far heavier than electrons. An electron has less than 1/2000th of the mass of a proton. This means the light particles that shape bonding and electricity contribute very little to the atom's weight. The nucleus, though tiny compared with the full atom, carries nearly everything that makes the atom massive. This explains why isotopes differ in mass when their neutron numbers change, even though their electron arrangements can remain nearly the same. It also shows why the nucleus became such an important focus in 20th century physics. Inside that compact region is the mass that anchors matter, the charge that defines elements, and the energy involved in nuclear change. The atom is therefore strangely divided. Its outer electrons control chemical personality, while its small central core carries almost all the substance. Protons decide the identity of every element in nature. Change the number of electrons, and an atom becomes an ion. Change the number of neutrons, and it becomes a different isotope. Change the number of protons, and it becomes a different element entirely. This number is called the atomic number, and it is the organizing principle behind the periodic table. 1 proton means hydrogen, 2 means helium, 6 means carbon. 79 means gold. The identity is not a matter of appearance or weight alone. It comes from the positive charge in the nucleus. That charge determines how many electrons a neutral atom will hold, which then shapes its chemical behavior. This is why adding or removing protons is not ordinary chemistry. It requires nuclear processes such as fusion, radioactive decay, or high-energy reactions. The proton count gives matter its elemental name and its place in nature's catalogue. Every piece of iron, every breath of oxygen, and every trace of gold is defined by that count. Neutrons help hold atomic nuclei together against electric repulsion. A nucleus contains positively charged protons, and positive charges repel one another. This raises an obvious question. How can several protons stay packed inside such a small space? Part of the answer is the strong nuclear force, which acts over very short distances. Neutrons are crucial because they contribute to this binding without adding electric repulsion. They help create a more stable arrangement between nucleons, which is the shared name for protons and neutrons. In light atoms, the numbers may be similar. In heavier atoms, more neutrons are needed to help offset the growing repulsion among many protons. Too few or too many neutrons can make a nucleus unstable, leading to radioactive decay. Neutrons also play key roles in nuclear reactors, stellar processes, and the creation of heavy elements. They carry no electric charge, yet their presence shapes the stability of matter. In the nucleus, the neutral particle is not passive. It is part of the reason atoms can exist. The strong force binds nuclei with extraordinary hidden power. Deep inside the atom, there is a force far stronger than electromagnetism at very short range. It acts between protons and neutrons and overcomes the repulsion that would otherwise push positively charged protons apart. Its reach is tiny, limited to distances within the nucleus, but within that realm, it is overwhelming. This is why nuclei can be stable, despite holding charges in close confinement. It is also why nuclear reactions can release such large amounts of energy. When nuclear particles rearrange into more tightly bound configurations, a small amount of mass can be converted into energy according to Einstein's famous relation. The strong force is not something we feel directly in ordinary life, yet it is buried inside every atom around us. It helps hold together the nuclei in the air, the ground, and the body. The everyday world rests on a force that is invisible, short-ranged, and astonishingly powerful. Electromagnetism controls how atoms bond and scatter light. Many of the most familiar features of matter come from one fundamental interaction. Electromagnetism governs the attraction between negatively charged electrons and positively charged nuclei. It also governs the repulsion between like charges. Because of it, electrons arrange themselves around nuclei, atoms attract or repel one another, and chemical bonds can form. The same interaction controls how light interacts with matter. When an electromagnetic wave reaches an atom, it can be absorbed, emitted, reflected, or scattered, depending on the atom's structure and the light's energy. This is why glass is transparent, metals shine, pigments show color, and the sky appears blue. Atomic physics reveals that these everyday experiences are not separate mysteries. They are connected expressions of charge, fields, and quantum states. Electromagnetism gives matter its chemistry and gives light its behavior in materials. It is the reason atoms do not simply pass through one another, and the reason the world is visible at all. Quantum tunneling lets particles cross barriers they should not cross. In ordinary experience, a barrier stops an object unless it has enough energy to climb over or break through. Quantum particles are different. Their wave nature gives them a small chance of being found on the other side of a barrier, even when classical physics says they lack the energy to cross it. This effect is called tunneling. It does not mean the particle digs a little hole. It means the particle's quantum state extends through the forbidden region, and sometimes the outcome appears beyond it. Tunneling is not just a curious idea. It is measured and used. It helps explain radioactive alpha decay, where particles escape from nuclei. It allows scanning tunneling microscopes to sense surfaces with atomic precision. It also plays a role in some electronic devices. The effect is strange because it challenges the hard boundary between possible and impossible. At tiny scales, nature allows a narrow chance for escape through the wall. Tunneling helps the sun shine by enabling nuclear fusion. At the sun's core, hydrogen nuclei move through an intensely hot plasma. They are positively charged, so they repel one another before they can get close enough for the strong nuclear force to bind them. Classical physics alone would make fusion far too rare at the sun's actual core temperature. Quantum tunneling changes the story. Because nuclei have wave properties, there is a small chance that they can pass through the electric barrier that keeps them apart. Once they are close enough, nuclear reactions can begin. Each individual event is unlikely, but the sum contains so many particles under such pressure that the process continues steadily. This is part of the reason our star can shine for billions of years rather than burning out quickly. The daylight reaching Earth depends on an effect that sounds almost impossible. The sun is powered not only by heat and gravity, but by the quantum permission for particles to cross a forbidden threshold. Atomic physics explains both starlight and the glow of lamps. The same principles can illuminate a galaxy and a bedroom. In a star, atoms and ions interact with radiation under extreme heat and pressure. Their spectral lines reveal composition, motion, and temperature. In a lamp, electrical energy excites atoms or shapes electron behavior in a material, producing light we can use. The settings could hardly be more different, yet the underlying rules belong to the same science. Energy changes inside matter produce photons. Atomic structure determines which photons appear. Interactions between light and charged particles decide what is absorbed, transmitted, or emitted. This unity is one of the most beautiful parts of physics. A glow from a distant star and a glow from a tube of gas can be understood through related ideas. The universe does not require separate rule books for the grand and the ordinary. Atomic physics connects them. It shows that light, whether cosmic or domestic, carries the signature of matter-changing energy. Photons are packets of light exchanged by atoms. Light behaves like a wave, yet it also arrives in discrete units. These units are called photons. When an atom drops from a higher energy state to a lower one, it can emit a photon carrying the energy difference. When an atom absorbs light, it takes in a photon whose energy matches an allowed transition. This idea helped solve puzzles that classical wave theory could not explain, especially the photoelectric effect and atomic spectra. A photon has no rest mass, but it carries energy and momentum. It can push matter, trigger chemical reactions, and transfer information across enormous distances. Every visible color corresponds to photons within a certain energy range. Radio waves, ultraviolet light, X-rays and gamma rays are also made of photons, though their energies differ. Atomic physics treats light as a messenger exchanged in exact amounts. Each photon is a tiny delivery of energy, and atoms accept or release those deliveries according to strict rules. An atom absorbs light only when the energy fits exactly. A beam of light can pass through a gas and leave certain colors missing. Those missing colors reveal that atoms in the gas absorbed photons of precise energies. The reason is that electrons in atoms have allowed states separated by exact energy differences. If a photon carries too little energy, it cannot produce that transition. If it carries too much, it may be ignored or cause a different process. This selectiveness is why absorption spectra have thin lines rather than smooth bites taken from every color. It is also why lasers, clocks, and spectroscopic instruments can be so accurate. Atoms are not vague receivers. They are tuned systems. Each one responds only to the frequencies that match its internal structure. The effect is similar to hearing a glass ring at one special pitch, except the atomic version is far more exact. Through this precision, light becomes a probe, and matter reveals the hidden spacing of its energy levels. Fluorescent materials glow after atoms store and release energy. When certain materials absorb high-energy light, their electrons are lifted into excited states. Very quickly, some of that energy is lost inside the material as heat or vibration. The remaining energy is then released as visible light. Because the emitted photon has less energy than the absorbed one, the glow often appears at a longer wavelength. This is why ultraviolet light can make some minerals, inks, or dyes shine in bright colors. The material is not simply reflecting the light that struck it. It is converting energy through atomic and molecular transitions. Fluorescence can be beautiful, but it is also practical. It is used in biological imaging, security markings, mineral identification, and certain lighting technologies. The glow usually stops almost as soon as the exciting light is removed, because the excited states decay quickly. A fluorescent object therefore seems to wake under the right illumination. Atomic physics explains how hidden energy can become visible color. Phosphorescent materials can keep glowing after the light is gone. Some materials do more than shine while they are being illuminated. They continue to emit light afterward, sometimes for minutes or hours. This happens because absorbed energy becomes trapped in longer-lived states. The release is delayed, so photons keep emerging after the original source is removed. Glow-in-the-dark paints and safety markings use this effect. They absorb energy from light, then give it back gradually. The process differs from ordinary fluorescence because the stored energy cannot return immediately by the easiest route. Quantum rules make the transition slower. This delay gives phosphorescent materials their memorable afterglow. They seem to remember the light. In reality, their atoms and molecules hold energy in states that release it over time. The effect is useful in dark corridors, emergency signs, watch dials, and toys. It also offers a simple lesson in quantum behavior. Matter can store a brief encounter with light and release it later as a visible trace. Lasers began as an idea about stimulated atomic emission. Long before laser pointers and fiber optic networks, the essential concept came from a theoretical insight. Einstein showed that an excited atom could be prompted by incoming radiation to emit a matching photon. This process, called stimulated emission, meant that light could be amplified if many atoms or molecules were prepared in the right excited condition. For decades, the idea remained a scientific possibility rather than a practical device. Researchers first developed masers, which amplified microwaves. Later, visible light versions became possible. The breakthrough required a gain medium, a way to excite it, and mirrors to build the light into a coherent beam. The result was so unusual that early lasers were sometimes described as solutions looking for problems. That changed quickly. Medicine, manufacturing, communication, measurement, and entertainment all found uses. The origin is still remarkable. A prediction about how atoms release light eventually became one of the most versatile technologies humans have ever built. The first laser used a ruby crystal full of atoms. In 1960, Theodore Maiman built a device that changed technology forever. Its heart was a synthetic ruby, a crystal made from aluminum oxide with a small amount of chromium inside it. Those chromium atoms were the key. When a powerful flash lamp pumped energy into the crystal, the atoms became excited. Mirrors at either end encouraged the light to bounce back and forth, growing stronger each time more atoms released matching photons. Then a narrow red beam burst out. At the time, the achievement seemed almost mysterious. It was not an ordinary lamp because the light was orderly, concentrated, and precise. It came from countless atomic events acting together. Ruby lasers soon found uses in research, medicine, and measurement. The story is wonderful because it shows how a jewel-like material became a doorway into a new age of light. A crystal that might have seemed decorative became the birthplace of one of physics' most powerful tools. Maser technology came before lasers and worked with microwaves. Before scientists learned to amplify visible light in a narrow beam, they achieved something similar with longer wavelength radiation. The maser was built to amplify microwaves by using stimulated emission. Its name came from the idea of microwave amplification. Early devices often used molecules such as ammonia, whose quantum states could be carefully selected and encouraged to emit radiation in step. This was a major breakthrough because it proved that controlled emission was not only theory, it could be engineered. Masers were extremely useful for precise measurements and sensitive detection. They later became important in radio astronomy, where faint signals from space require extraordinary care. In nature, maser action can even occur in cosmic gas clouds, producing intense microwave signals that travel across interstellar distances. The maser may be less famous than the laser, but it was an essential older sibling. It showed that quantum control could turn invisible transitions into a practical source of remarkably pure radiation. Atomic clocks use cesium atoms to define the second. The modern second is not based on the swing of Earth or the motion of the Sun. It is based on a transition inside cesium atoms. In a cesium clock, atoms pass through a region where microwave radiation is tuned to match a very specific change between two hyperfine states. When the radiation is exactly right, the atoms respond in a predictable way. The clock continually adjusts the microwave frequency until it matches the atomic transition with extreme precision. That frequency defines the second through a fixed number of cycles. This gives timekeeping an anchor in the behavior of matter itself, rather than in astronomy, which is affected by slow changes in Earth's rotation. Cesium clocks became the foundation of international time standards because atoms of the same isotope behave identically anywhere. A cesium atom in one laboratory follows the same rules as a cesium atom across the world. Time, in this system, is counted by nature's own rhythm. Some optical atomic clocks could lose 1 second in billions of years. The newest generation of atomic clocks can use transitions at optical frequencies, which are much higher than microwave frequencies. A higher frequency gives more cycles to count, and that can make the measurement far more precise. These clocks may use atoms such as strontium or ytterbium, often held in carefully controlled traps made of laser light. Scientists compare the clock's laser to the atom's transition and adjust it until the match is nearly perfect. The accuracy is astonishing. Some designs are so stable that, if they could run unchanged across immense spans of time, their error would amount to less than a second over billions of years. This level of precision is not just a triumph of timekeeping. It lets researchers test whether fundamental constants change, compare gravity between locations, and search for subtle physics beyond current theories. The clocks are so sensitive that time itself becomes an instrument for exploring the universe. Better atomic clocks can measure changes in height through gravity. Einstein's theory of relativity says that time does not pass at exactly the same rate everywhere. A clock at a higher altitude, where gravity is slightly weaker, ticks a little faster than one lower down. For most of daily life, the difference is far too small to notice. Modern atomic clocks are precise enough to detect it. If two excellent clocks are placed at different heights, their rates can reveal a change of elevation. This means timekeeping can become a tool for measuring gravity's shape near Earth's surface. In the future, networks of such clocks may help map underground water, magma movement, or changes in ice sheets by sensing tiny variations in gravitational potential. The idea is startling. A clock can become a kind of ruler, and seconds can reveal altitude. Atomic physics and relativity meet in this achievement. The ticking of atoms becomes sensitive to the curve of space-time around our planet. GPS satellites depend on atomic timing to locate you accurately. Navigation from space works by timing signals with extraordinary care. A receiver on Earth listens to several satellites, each broadcasting when its signal was sent and where the satellite was. Because radio signals travel at the speed of light, even a tiny timing error can become a large position error. Atomic clocks aboard satellites provide the needed stability. Relativity also matters. Satellite clocks experience weaker gravity than clocks on Earth, which tends to make them tick faster. Their motion has another effect that makes them tick slower. Engineers account for both. Without these corrections, GPS positions would quickly drift and become useless. So every time a phone finds a route or a ship checks its location, it depends on atomic transitions and relativistic physics working together. This is one of the most surprising links between deep science and everyday life. Your map app is not just using satellites. It is using the measured behavior of atoms in orbit. Cold atoms can behave like a single quantum wave. At ordinary temperatures, atoms race in many directions with many different speeds. Their quantum wave properties are present, but they are usually hidden by restless motion. When atoms are cooled to extremely low temperatures, their motion slows dramatically, and their wave nature becomes easier to see. Under special conditions, many atoms can enter the same quantum state. Instead of acting like separate tiny particles, they begin to behave as one collective wave. This is not a metaphor for cooperation. It is a measurable physical state. Interference patterns, fluid behavior, and collective responses reveal that the atoms share a single quantum description. Such systems allow scientists to study matter in a form that does not appear in everyday life. They become laboratories for quantum mechanics on a visible scale. Cold atoms can model magnetism, fluid flow, and other complex physics. When matter is chilled almost to stillness, it stops looking ordinary and begins to reveal its wave-like identity. Bose-Einstein condensates form when atoms become extremely cold. This state of matter was predicted long before it was created in the laboratory. Satyendra Nath Bose and Albert Einstein showed that certain particles could crowd into the same lowest energy state if cooled enough. Decades later, scientists achieved this with dilute gases of atoms chilled to temperatures just above absolute zero. At that point, many atoms lost their individual thermal motion and merged into a collective quantum state. The result is a Bose-Einstein condensate. It can flow in unusual ways, respond as one coherent matter wave, and display quantum effects on a scale large enough to image. Creating one requires careful cooling and trapping, because ordinary contact with a warm surface would destroy it. The achievement opened a new field of research. It allowed scientists to study superfluidity, quantum vortices, and simulated condensed matter systems with remarkable control. The condensate feels almost impossible because it is matter behaving with a unity usually associated with light. Laser cooling slows atoms with carefully tuned light. Light can push matter, even though the push is tiny. Scientists use this effect to slow atoms. a laser is tuned slightly below an atomic transition. When an atom moves toward the beam, the light appears shifted into resonance because of the Doppler effect. The atom absorbs a photon and receives a small push opposite its motion. It then emits a photon in a random direction. Repeated many times from several directions, this process reduces the atom's speed. Slower atoms mean lower temperature. The method is subtle because the laser must be tuned with great precision. Too much energy or the wrong frequency will not cool the atoms properly. Laser cooling made possible many of the most delicate experiments in modern atomic physics. It helps create cold gases, improve clocks, and prepare atoms for quantum research. The image is remarkable. Beams of light, which we usually imagine as weightless, can gently break atoms until they nearly stop. Magnetic traps can hold atoms without touching any walls. Atoms are easily disturbed by contact with ordinary surfaces. A wall can warm them, scatter them, or destroy the delicate state being studied. Magnetic traps solve this by holding atoms in open space. Certain atoms act like tiny magnets because of their internal angular momentum. In a carefully shaped magnetic field, they feel forces that guide them toward regions of lower or higher field strength, depending on their state. The result is a container made not from glass or metal, but from invisible field geometry. This allows scientists to keep atoms suspended while they are cooled, manipulated, and measured. Magnetic trapping became crucial for creating ultra-cold gases and Bose-Einstein condensates. It also showed how deeply atomic properties can be used as handles, even when the atoms themselves cannot be touched. The trap is not a cage in the usual sense. It is a landscape of magnetic energy, shaped so that atoms remain gently confined in midair. Scientists can arrange individual atoms into tiny artificial patterns. The ability to position atoms one by one is one of the great achievements of nanoscience. Using specialized instruments, researchers can move atoms across surfaces and create patterns smaller than anything visible by ordinary means. Sometimes the goal is to study basic physics. Sometimes it is to build artificial structures that behave differently from natural materials. The process is painstaking. Atoms may be nudged by the tip of a scanning probe, guided by electrical interactions, or held in optical arrays. When arranged precisely, they can form letters, rings, lattices, or experimental systems that mimic more complex matter. This is not manufacturing in the ordinary sense. It is closer to constructing with the smallest possible pieces of chemical identity. Such experiments reveal how surfaces, bonds, and quantum states change when matter is organized at the atomic scale. They also hint at future technologies where information and function may be built from individual atoms placed with deliberate care. Scanning tunneling microscopes can feel atoms on a surface. This instrument does not see atoms with ordinary light. Instead, it uses a needle-like tip brought extremely close to a conducting surface. When the gap is small enough, electrons can tunnel between the tip and the surface. The tunneling current depends very sensitively on distance. If the tip moves over an atom, the current changes. By scanning across the surface and adjusting the tip, scientists build a map of atomic scale features. The result can look like an image, but it is really a record of quantum tunneling and electronic structure. This invention gave researchers an unprecedented way to study surfaces. It also allowed them to move individual atoms under controlled conditions. The power of the method comes from its delicacy. A change much smaller than the width of an atom can alter the measured current. The microscope feels the surface through the quantum chance of electrons crossing a gap, turning an invisible effect into a practical sense of touch. The famous quantum corral was built from individual iron atoms. In 1993, researchers arranged iron atoms on a copper surface into a tiny ring. The structure became known as a quantum corral. It was not just a display of atomic control. It revealed how electrons on the surface behaved like waves confined inside a boundary. The iron atoms acted like walls that scattered the surface electrons, producing standing wave patterns inside the ring. Images from a scanning tunneling microscope showed ripples that looked almost like waves in a pond, though they were patterns of quantum probability and electronic density. The experiment made an abstract idea feel visible. Electrons in materials are not simply little particles moving through empty space. They can form wave patterns shaped by atomic arrangements. The quantum corral became iconic because it combined precision, beauty, and deep physics. Scientists had placed atoms like fence posts and watched matter's wave nature appear inside the enclosure. Rydberg atoms are enormous compared with ordinary atoms. When an electron in an atom is excited to a very high energy level, it can move far from the nucleus in a loose, extended state. Such an atom is called a Rydberg atom. Compared with ordinary atoms, it can be gigantic. The electron is still bound, but only weakly, and its orbit-like quantum state extends over a much larger region. This makes the atom extremely delicate. Small electric fields, nearby charges, or interactions with other atoms can strongly affect it. Rydberg atoms are useful because their exaggerated properties make quantum behavior easier to manipulate. They are studied in precision spectroscopy, quantum simulation, and emerging quantum technologies. They also help scientists explore how atoms interact when their outer electrons are spread across large distances. A Rydberg atom is like an atom turned up to an extreme setting. Its inner core remains tiny, but its outer electron reaches outward in a way that makes the whole system unusually large and responsive. Some excited atoms can grow almost the size of bacteria. In specially prepared states, an atom can become astonishingly large. This happens when an electron is lifted into a very high Rydberg level, where its quantum state extends far from the nucleus. The atom remains an atom because the electron is still bound to the core, but the distance involved can become enormous by atomic standards. The scale can approach that of small biological cells. This stretches the everyday meaning of an atom. We often imagine atoms as uniformly tiny, but quantum mechanics allows some excited states to expand dramatically. Such atoms are fragile and short-lived under ordinary conditions. They must be created and studied in controlled environments. Their size gives them strong interactions with electric fields and with one another, which makes them valuable for experiments. They help bridge the gap between the microscopic and the almost visible. An atom in one state may be compact, while another version of the same element can swell into a giant quantum structure. Rydberg atoms are so sensitive that tiny fields disturb them. Because the outer electron in a Rydberg atom is weakly bound and far from the nucleus, the whole atom responds strongly to electric and magnetic influences. A field that would barely affect an ordinary atom can shift the energy levels of a Rydberg atom noticeably. This sensitivity makes them powerful probes. Scientists can use them to detect microwave fields, study tiny electric disturbances, and explore interactions between atoms over relatively long distances. Their responsiveness also creates challenges. Stray fields in the laboratory must be controlled carefully, or the atoms will give misleading results. Yet that same delicacy is what makes them exciting. They turn faint environmental effects into measurable changes. In quantum information research, interactions between nearby Rydberg atoms can be used to control whether certain states are allowed or blocked. In a sense, these atoms are like ultra-sensitive antennas made from matter itself. Their fragility is not a weakness. It is the source of their usefulness. Ion traps can hold charged atoms for extraordinary experiments. When an atom loses or gains an electron, it becomes an ion. Because ions carry electric charge, they can be confined using electric fields. In an ion trap, carefully arranged electrodes create forces that keep charged atoms suspended in a small region of space. Some traps also use radio frequency fields to stabilize the motion. Once held, ions can be cooled with lasers and manipulated with extreme precision. They can remain isolated from the outside world long enough for researchers to study their internal states, build quantum logic operations, or make highly accurate clocks. The trapped ion is not resting on a surface. It floats in a controlled electromagnetic environment. This isolation is what makes the technique so valuable. It allows one atom, or a chain of atoms, to become a carefully prepared quantum system. Ion traps turn charged atoms into experimental subjects that can be observed, addressed, and controlled with a level of care that once seemed unreachable. Single trapped ions are among the best quantum clocks ever made. A lone ion held in a trap can serve as an exceptionally clean reference for time. Because it is isolated from many disturbances, scientists can probe one of its narrow optical transitions with great precision. Lasers are tuned until they match the transition, and the resulting frequency becomes the clock's heartbeat. Ions such as aluminum, mercury, or ytterbium have been used in advanced designs. The advantage is control. The ion can be cooled to reduce motion, shielded from unwanted fields, and measured repeatedly. Even tiny shifts must be understood, including effects from motion, electromagnetic fields, and blackbody radiation. The reward is extraordinary accuracy. A single atom, suspended by fields and interrogated by light, can outperform older timekeeping systems by wide margins. This is one of the most elegant ideas in measurement. Instead of building a larger clock, scientists make the clock smaller, cleaner, and closer to a fundamental property of nature. Quantum computers can use atoms as delicate information carriers. In ordinary computing, information is stored in bits that take values such as 0 or 1. In quantum computing, the basic units are qubits, which can be encoded in carefully chosen atomic states. Neutral atoms, trapped ions, and other atomic systems can all serve this purpose. The states must be controlled with lasers, microwaves, or electromagnetic fields. They must also be protected from random disturbances that would erase their quantum information. The attraction is powerful. Atoms of the same isotope are naturally identical, which makes them excellent candidates for reproducible qubits. Trapped ions can be linked through shared motion. Neutral atoms can be arranged in large arrays using light. The challenge is maintaining coherence while performing useful operations. Even so, atomic platforms have produced some of the most impressive demonstrations in the field. The idea feels almost magical. Information can be held in the internal state of a single atom and processed through the laws of quantum mechanics. Qubits can exist in mixed states before they are measured. A quantum bit is not limited to being simply one state or another before measurement. It can be prepared in a superposition where its state contains a combination of possibilities. For an atomic qubit, those possibilities might correspond to two different internal energy states. When measured, the result is one definite outcome. But before measurement, the quantum description can include both with particular amplitudes. This is not just ignorance about a hidden ordinary value. Experiments show that superposition leads to interference, which affects measurable outcomes in ways classical uncertainty cannot reproduce. This is one reason quantum computing may solve certain problems differently from classical computing. The qubit's power comes from the controlled evolution of these amplitudes before the final readout. The delicacy is extreme. Unwanted interaction with the environment can turn quantum possibility into ordinary randomness. The strange pre-measurement state is therefore both a resource and a challenge. It must be created, guided, and protected. Entangled atoms can share one quantum state across distance. Entanglement is one of the most surprising features of quantum mechanics. When two atoms become entangled, their properties are described by a shared state rather than by separate individual states. Measurements on one atom are then correlated with measurements on the other in ways that cannot be explained by ordinary shared instructions. This remains true even when the atoms are separated, provided the entanglement is preserved. The effect disturbed Einstein, who worried about what it suggested regarding locality and reality. Later experiments showed that quantum correlations are real and stronger than classical physics allows. Entanglement is now treated as a practical resource. It can help with quantum communication, quantum computing, and precision measurement. Creating it between atoms requires careful control, often through photons, shared motion, or controlled interactions. The idea is profound. Two small pieces of matter can no longer be fully described alone. Their deepest description belongs to the pair. Measurement changes what can be known about an atomic system. In classical life, measurement can seem passive. You check a temperature, read a distance, or weigh an object. In quantum physics, measurement plays a more active role. An atom can be prepared in a state that includes several possible outcomes for a property. When a measurement is made, the result becomes definite, and the state is changed by the act of obtaining that information. This is not merely because instruments are clumsy. It is built into the theory and confirmed by experiment. Measuring one property sharply can limit what can be known about another. Detecting which path a particle takes can destroy an interference pattern. In atomic systems, this makes observation part of the story. Scientists must decide what to measure and how strongly to measure it. The result is a view of nature, where knowledge is not simply uncovered like a hidden label. At small scales, asking a question can reshape the answer. Heisenberg showed that precision has a deep natural limit. Werner Heisenberg's uncertainty principle revealed that some pairs of physical properties cannot both be known with unlimited precision. Position and momentum are the famous example. The more precisely one is specified, the less precisely the other can be known. This is not a flaw in instruments. It is a feature of quantum systems. For an electron in an atom, the principle helps explain why it cannot be treated as a tiny planet with a precise orbit. If it were confined too sharply near the nucleus, its momentum would become highly uncertain. The principle is often misunderstood as simple disturbance caused by measurement, but its meaning is deeper. Quantum states do not possess all classical properties with exact values at the same time. This changed the philosophy of physics. It set a boundary on the old dream of complete mechanical prediction. Nature still follows laws, but those laws speak in wave functions, probabilities, and limits on simultaneous knowledge. Schrödinger's equation predicts how atomic wave functions unfold through time. At the heart of non-relativistic quantum mechanics is an equation that describes how a system's wave function changes. For atoms, it allows scientists to calculate allowed energy levels, probability distributions, and transitions. Erwin Schrödinger introduced it in the 1920s, and it quickly became one of physics' central tools. When applied to hydrogen, it explained the atom's structure in a far richer way than the old orbit model. It showed why orbitals have particular shapes and energies. For more complex atoms, exact solutions become difficult, but approximations and computational methods still rely on the same underlying framework. The equation does not track a particle like a dot moving along a path. It tracks the evolution of a quantum state. That shift was revolutionary. The future of an atomic system could be predicted with extraordinary accuracy, but the prediction concerned probabilities until measurement occurred. Schrödinger's work gave atomic physics a mathematical language that remains indispensable. Dirac's theory predicted antimatter from the mathematics of electrons. Paul Dirac wanted an equation that described electrons while respecting both quantum mechanics and special relativity. The result was beautiful, but it contained something unexpected. Its solutions implied the existence of a particle like the electron, but with opposite charge. This was not added to the theory by hand. It emerged from the mathematics. A few years later, the positron was discovered in cosmic ray experiments, confirming that antimatter was real. This was a spectacular moment in physics. A demand for mathematical consistency had revealed a new kind of matter. Dirac's work also explained electron spin naturally and laid foundations for later quantum field theory. Antimatter is now used in medical imaging through positron emission tomography, and it remains important in studies of fundamental symmetry. The story is captivating because it shows that equations can sometimes see farther than experiments. By following the logic of the electron, Dirac opened a door to its mirror counterpart. Positronium is a strange atom made from matter and antimatter. Imagine an atom with no proton at its center. Positronium consists of an electron and a positron bound together by electric attraction. The positron is the electron's antimatter counterpart, carrying positive charge. Because the two particles have equal mass, they orbit their shared center rather than one orbiting a heavy nucleus. The system is short-lived because matter and antimatter can annihilate, turning their mass into photons. Even so, positronium lasts long enough to be studied. It is valuable because it is relatively simple and sensitive to the rules of quantum electrodynamics. Its energy levels and decay rates let physicists test how accurately theory describes the electromagnetic interaction. Positronium can also form unusual states and has been investigated in connection with precision measurements and antimatter research. It feels like a paradoxical object. It is an atom that contains its own disappearance, a delicate partnership between opposites that can exist briefly before becoming pure radiation. Muonic atoms shrink because muons are much heavier than electrons. A muon has the same negative electric charge as an electron, but it is far more massive. If a muon replaces an electron in an atom, it orbits much closer to the nucleus. The resulting muonic atom is dramatically smaller in its inner structure. This closeness makes the muon highly sensitive to the size and shape of the nucleus. Scientists use muonic atoms to measure nuclear charge radii with great precision. They have also revealed puzzles, such as disagreements in measurements of the proton size that pushed researchers to re-examine assumptions and experimental details. Muons do not last long, so these atoms are temporary. Their brief existence still provides a powerful window into nuclear structure. They show how changing just one particle can transform an atom's scale and behavior. The familiar element can become a compact exotic system, where the usual electron cloud is replaced by a heavier visitor circling nearer to the atomic core. Exotic atoms help scientists test the deepest rules of physics. Not all atoms follow the familiar pattern of electrons around nuclei. Some contain unusual particles, such as muons, pions, antiprotons, or positrons. These systems are often short-lived, but they can be extraordinarily informative. Because their properties depend on the same fundamental interactions that govern ordinary matter, precise measurements can test whether theories are complete. Exotic atoms may reveal nuclear sizes, antimatter behavior, or subtle effects from quantum electrodynamics. They are created in specialized laboratories where rare particles can be slowed and captured. The experiments are difficult because the atoms may decay or annihilate quickly, yet that difficulty is part of their value. They place matter under unusual conditions and expose effects that ordinary atoms may hide. Studying them is like asking nature the same question in a different accent. If the answer changes unexpectedly, it may point to new physics. These strange atoms are not curiosities alone. They are precision instruments built from the edges of the particle world. Anti-hydrogen atoms have been made and trapped in laboratories. Hydrogen has one proton and one electron. Its antimatter counterpart contains an antiproton and a positron. Creating it is difficult because antimatter is rare on Earth and annihilates when it touches ordinary matter. Scientists must first produce antiprotons, slow them down, combine them with positrons, and then hold the neutral antiatoms without letting them hit the walls. Because antihydrogen has no net electric charge, trapping it requires magnetic techniques that act on its internal magnetic properties. The achievement is extraordinary. It allows researchers to compare hydrogen and antihydrogen with great precision. According to fundamental symmetry principles, their spectral properties should match exactly. Any confirmed difference would be a major clue that current physics is incomplete. Making antihydrogen is not just about producing a mirror version of the simplest atom. It is a way to ask why the universe contains so much matter and so little antimatter. A trapped antiatom becomes a quiet test of cosmic history. Studying antihydrogen may reveal whether antimatter falls like matter. Gravity is familiar for ordinary matter, but testing it directly with antimatter is extremely challenging. Antihydrogen offers a path because it is electrically neutral, so electric fields do not overwhelm its motion as easily as they would for charged antiparticles. Researchers can trap antihydrogen atoms, release them, and observe how they move under Earth's gravity. The expectation from general relativity is that antimatter should fall downward like matter. Recent experiments support that expectation, but improving precision remains important. If antimatter behaved even slightly differently, it would shake the foundations of physics. The experiment is delicate because antihydrogen atoms are produced in small numbers, held at low energies, and easily lost to annihilation on contact with material surfaces. Watching them fall is therefore not as simple as dropping a ball. It requires years of control over some of the rarest atoms ever made. The question sounds almost childlike, yet its answer reaches into the deepest symmetries of nature. Atomic transitions can test whether nature's constants stay constant. Some questions in physics sound almost too large to test. One of them asks whether the basic constants of nature have always had the same values. Atomic physics gives scientists a way to investigate this without reaching back in time by hand. Different atomic transitions depend on constants such as the fine structure, constant in slightly different ways. By comparing extremely precise clocks over long periods, researchers can look for tiny drifts in their relative ticking. Astronomers can also study ancient light from distant gas clouds, because that light carries spectral patterns from the past. If the lines were shifted in ways not explained by motion or expansion, it could suggest that atomic rules were once subtly different. So far, no confirmed change has overturned the standard picture. Yet the test is profound. Atoms become witnesses to the stability of reality. Their transitions ask whether the same rules that govern a laboratory today also governed matter when the universe was young. Tiny shifts in atomic spectra revealed quantum electrodynamics. When physicists measured atomic spectra with greater and greater precision, they found details that earlier theories could not fully explain. The lines were not always exactly where simple calculations predicted. These small differences were not mistakes. They were clues. Quantum electrodynamics, often called QED, emerged as the theory describing how charged particles interact through photons. It accounts for effects that arise because electromagnetic fields are quantized. Electrons are influenced not only by the nucleus and by light, but also by subtle quantum processes that appear and disappear according to the rules of the field. The beauty of QED is its accuracy. It can predict some quantities to astonishing precision, matching experiments in ways that made it one of the great triumphs of 20th century physics. The lesson is striking. A tiny shift in a spectral line can open a vast theoretical world. Nature sometimes reveals its deepest machinery through differences so small they demand extraordinary care to notice. The Lamb shift showed empty space is not truly empty. In the 1940s, Willis Lamb measured a small energy difference in hydrogen that Dirac's earlier theory had not predicted in the expected way. The discovery became known as the Lamb shift. Its explanation required a new understanding of the vacuum. Empty space, in quantum field theory, is not a simple blank. It is filled with fluctuating fields that can influence particles. An electron in an atom interacts with these fluctuations, and that changes its energy slightly. The shift is small, but it is measurable. This was a major success for quantum electrodynamics because the theory could calculate the effect and match observation. The result transformed the meaning of nothingness. Vacuum became an active physical state, not a lifeless absence. In a hydrogen atom, one of nature's simplest systems, scientists found evidence that empty space itself has structure. A tiny correction in energy became proof that the quietest background in physics is still alive with quantum activity. Vacuum fluctuations can subtly nudge the energy of atoms. Quantum theory says fields cannot be perfectly still, even in their lowest energy state. These restless fluctuations affect particles and atoms in measurable ways. An electron bound to a nucleus is not isolated from the electromagnetic field around it. It is constantly coupled to that field, and the field's quantum behavior slightly alters the atom's energy levels. These effects are usually tiny, but precision spectroscopy can detect them. They matter especially in simple atoms, where theoretical predictions can be compared with measurements in exacting detail. Vacuum fluctuations also contribute to how excited atoms emit light. They help explain why spontaneous emission happens at all, because the atom interacts with the ever-present quantum field. This is one of those ideas that makes physics feel startlingly deep. Even when every lamp is off and every ordinary source of radiation is removed, the quantum vacuum still participates. Atoms do not sit inside emptiness. They sit inside a sea of underlying field activity. The Casimir effect shows quantum fields can create measurable force. Place two uncharged metal plates extremely close together in a vacuum, and a tiny attraction can appear between them. This is the Casimir effect. It arises because quantum fields between the plates can support only certain modes, while outside the plates more modes are available. The imbalance creates a measurable force. The effect is small, but in microscopic systems it can matter. It is often described as evidence that the vacuum has physical consequences. This does not mean energy can be taken freely from empty space in the way science fiction might suggest. It means that the permitted fluctuations of quantum fields depend on boundaries, and those boundaries can feel a force. The Casimir effect has been measured with careful experiments, and it remains important in nanotechnology because tiny components can be affected by surface forces. It is a remarkable thought. Two plane surfaces, separated by almost nothing, can reveal the presence of quantum fields in the space between them. Atomic physicists can use light to push matter gently. Light has momentum, which means it can exert pressure. For everyday objects, the effect is almost unimaginably small. For atoms, it becomes useful. When an atom absorbs a photon, it receives a tiny kick in the photon's direction. When it emits light again, the recoil changes its motion. By arranging laser beams carefully, scientists can slow, steer, or confine atoms with delicate control. The forces are not muscular, yet they are precise. They allow researchers to cool atomic gases, guide atomic beams, and prepare matter for quantum experiments. Radiation pressure also appears in space, where sunlight can influence dust grains and spacecraft with reflective sails. At the atomic scale, though, the effect becomes an instrument of great refinement. A beam of light can act like a hand without touching. It can move matter by transferring momentum one photon at a time. The idea turns light from something we see into something that can also shape motion. Optical tweezers can hold tiny particles with focused light. A highly focused laser beam can trap small objects near the brightest part of the light field. The electric field of the light induces a response in the particle, and the resulting force draws it toward the focus. This technique is called optical tweezing. It has been used to hold microscopic beads, biological molecules, and even individual atoms under the right conditions. The power of the method is that it can manipulate delicate objects without mechanical contact. In biology, optical tweezers have measured forces produced by molecular motors. In atomic physics, arrays of focused laser spots can hold neutral atoms in ordered patterns for quantum simulation and computation. The trap is invisible except for the light itself, yet it can act with remarkable control. This is a beautiful reversal of expectation. A laser, often imagined as a tool for cutting or burning, can also behave like the gentlest pair of fingers, holding a particle in place through the pressure of light. Laser light can sort atoms by their quantum state. Atoms of the same element can still differ in their internal quantum states. They may have different spin orientations, energy levels, or magnetic properties. Laser light can be tuned to interact with one state more strongly than another. This allows scientists to separate, prepare, or detect atoms based on their internal condition. In some experiments, a laser pushes only atoms in a particular state, leaving others almost untouched. In others, light transfers atoms into selected states, so the sample becomes cleaner and more controlled. This ability is essential for precision clocks, quantum computing, and studies of ultra-cold gases. It turns light into a filter that reads the hidden identity of an atom without needing a label. The method also shows how precise atomic physics can be. Two atoms may look identical in every ordinary way, yet a carefully tuned beam can tell them apart. Their quantum state becomes something that can be selected, guided, and measured. Atom interferometers use matter waves to measure motion precisely. Interference is often associated with light, but atoms also have wave properties. An atom interferometer splits an atomic matter wave into two paths, lets the paths experience different conditions, and then recombines them. The resulting pattern depends on acceleration, rotation, gravity, and other influences along the paths. Because atomic wavelengths can be extremely short and the measurements very stable, these instruments can detect tiny changes in motion. They are used in precision tests of physics and are being developed for navigation, gravity mapping, and measurements that may not require external signals like satellites. The idea is striking because the atoms are not merely moving objects. Their quantum waves act as measuring devices. A small change in the world shifts the phase between the paths, and that shift appears when the waves meet again. Atom interferometry turns matter itself into a ruler for motion. It measures not by gears or springs, but by the delicate recombination of quantum possibilities. Matter waves let atoms interfere with themselves like ripples. In the early 20th century, Louis de Broglie proposed that particles of matter have wavelengths. This was a bold extension of wave-particle duality. Later experiments confirmed it by showing that electrons, neutrons, atoms, and even larger molecules can produce interference. When an atom's wave function is split and later recombined, the paths can add or cancel like water ripples. The strange part is that this can happen even when atoms pass through an experiment, one at a time. Each detection is localized, but the overall pattern reveals wave behavior. This challenges the ordinary belief that only light can interfere. Matter is wave-like too, though the effect is usually hidden for large, warm objects. The discovery reshaped physics because it meant atoms could not be understood only as little balls. Their motion had a wave aspect that could be measured and used. Matter waves now support precision instruments and deepen our understanding of quantum reality. Atomic beams helped reveal the quantized nature of spin. In early atomic beam experiments, researchers sent atoms through carefully shaped magnetic fields and watched how the beams split. The results showed that certain atomic properties could take only discrete orientations rather than a continuous range. This was crucial evidence for quantization beyond energy levels. Spin emerged as a new kind of intrinsic angular momentum. It was not simply a tiny object rotating like a top. It was a quantum property with allowed measurement outcomes. Atomic beams were powerful because they allowed scientists to study particles in flight, away from many disturbances found in bulk materials. By separating atoms according to their magnetic behavior, the experiments made invisible internal structure visible on a screen. They showed that the microscopic world is not merely smaller than the everyday world. It is organized differently. Direction, magnetism, and angular momentum can come in permitted values, and atoms reveal those values when they pass through the right field. The Stern-Gerlach experiment split atoms by magnetic orientation. In 1922, Otto Stern and Walther Gerlach fired silver atoms through a non-uniform magnetic field. Classical physics suggested the atom's magnetic orientations should produce a continuous smear on the detector. Instead, the beams split into distinct spots. The results showed that the atom's angular momentum along the measurement direction had quantized values. At the time, the full idea of electron spin had not yet been developed, but the experiment became a landmark in quantum physics. It demonstrated that measurement can force a quantum system into specific outcomes. The silver atoms did not arrive with every possible magnetic orientation marked across the screen. They appeared in separated groups. This helped scientists understand that certain properties are not continuous at atomic scales. The experiment was simple in outline, but profound in meaning. A beam of neutral atoms, a magnetic field, and a detector revealed that nature sometimes answers yes or no where classical physics expected every shade in between. Electron spin is not ordinary spinning, but quantum identity. The word spin can be misleading. An electron is not a tiny ball rotating around an axis in the usual mechanical way. Its spin is an intrinsic quantum property, like charge or mass. It gives the electron angular momentum and a magnetic moment, which means it responds to magnetic fields. Spin has allowed values, and measurements along a chosen direction produce definite outcomes. This property helps explain atomic structure, chemical behavior, magnetism, and many technologies. It is also central to quantum information, why spin states can encode qubits. The difficulty is that there is no perfect everyday picture for it. If you imagine literal spinning, you run into contradictions. Instead, spin must be accepted as part of the quantum description of particles. It is not a motion added to the electron. It is built into what the electron is. This makes it one of the clearest reminders that the smallest parts of matter do not need to resemble familiar objects. Spin helps explain magnetism in atoms and materials. Magnets feel familiar, but their origin reaches into quantum physics. Electrons have spin, and spin gives them tiny magnetic moments. In many materials, these moments point in random directions, so their effects cancel. In ferromagnetic materials such as iron, interactions between electrons can cause many moments to align. When enough of them point the same way, their combined effect produces a magnetic field we can feel and measure. Atomic orbitals can also contribute to magnetism, but spin is often central. This explains why magnetism depends so strongly on electronic structure. It is not just a property of metal as a bulk substance. It comes from countless quantum moments arranging themselves in matter. Temperature can disrupt that order, which is why a magnet can lose its magnetism when heated above a certain point. The everyday pull of a refrigerator magnet is therefore a large-scale expression of electron spin. A quiet quantum property becomes a force strong enough to hold paper in place. Hyperfine structure comes from tiny interactions inside atoms. Atomic energy levels are not always single, clean steps. With sufficiently precise measurements, each level can split into smaller sublevels. Hyperfine structure arises mainly from interactions between the magnetic properties of the nucleus and the electrons. The nucleus may have spin, and the electrons respond to it. These effects are much smaller than ordinary electronic energy differences, but they are enormously important. The famous cesium-Klopp transition comes from hyperfine splitting. Radio astronomers also study a hyperfine transition in neutral hydrogen, which produces a wavelength of about 21 centimeters. That signal has helped map gas across the Milky Way. Hyperfine structure shows that even a simple atom has layers of detail. The nucleus is not just a heavy point at the center. Its internal properties can subtly shape the atom's spectrum. Precision instruments can detect these tiny splittings, and those measurements become clocks, maps, and tests of fundamental theory. Small interactions can become large tools. The hydrogen maser uses atomic transitions to keep steady time. A hydrogen maser relies on a very stable transition in hydrogen atoms. The atoms are first prepared so that those in a desired state enter a resonant cavity. Inside, they can emit microwave radiation in a highly controlled way. The resulting signal is extremely stable over short and medium time spans, which makes hydrogen masers valuable in observatories, deep space communication, and timekeeping systems. They are often used where low noise and high frequency stability are essential. The device is a beautiful example of atomic regularity, becoming a practical reference. Hydrogen is the simplest atom, yet its internal structure contains transitions precise enough to support advanced technology. The maser does not tick with gears or vibrating metal. It produces a steady microwave signal based on a quantum change inside atoms. In radio astronomy, such stability helps combine signals from widely separated telescopes. A transition in hydrogen can therefore support measurements that span continents and reach far into space. Atomic vapor cells can detect magnetic fields with great sensitivity. A vapor cell contains a gas of atoms, often an alkali metal such as rubidium or cesium, sealed inside a small glass container. When light passes through the vapor, the atom's response can change depending on the magnetic field around them. By monitoring that optical response, scientists can measure fields with impressive sensitivity. These devices are called atomic magnetometers. They can operate without the cryogenic cooling required by some other sensitive magnetometers, which makes them useful in many settings. They can detect tiny biomagnetic signals from the brain or heart, search for hidden objects, and support fundamental physics experiments. The principle is elegant. A magnetic field slightly shifts how atomic spins and energy levels behave. Light reads that shift. The atoms become the sensing element, and their quantum properties provide the calibration. A little sealed vapor, when interrogated carefully, can act as an exquisitely sensitive compass for fields far weaker than a refrigerator magnet. Some atomic sensors can measure gravity without moving parts. Traditional gravimeters often depend on mechanical components such as springs or falling masses. Atomic sensors can use a different approach. They measure how atoms fall or how their matter waves shift in a gravitational field. In atom interferometer gravimeters, clouds of cold atoms are launched or dropped, then manipulated by laser pulses that split and recombine their quantum wave functions. Gravity changes the phase between the paths, and that phase reveals the local gravitational acceleration. Because the measurement is tied to atomic properties and laser frequencies, it can be very stable and precise. Such sensors may help detect underground cavities, monitor volcanic regions, improve navigation, or measure changes in water storage beneath the ground. They do not sense gravity by feeling weight in the ordinary way. They sense it by watching how freely falling atoms accumulate quantum phase. This turns gravity from a pull on a mechanical object into a measurable imprint on matter waves. Quantum jumps were once theoretical, then watched in real atoms. Early quantum theory proposed that atoms change energy in sudden jumps rather than smooth slides. For many years, this was inferred from spectra and theory, rather than directly seen in individual systems. Later, experiments with trapped ions made the jumps visible in a dramatic way. A single ion could be made to fluoresce under laser light, glowing as it scattered photons. When it entered a different state, the glow suddenly stopped. Then it returned. The atom seemed to blink, revealing transitions between quantum states in real time. This was a powerful moment because it turned an abstract idea into an observed event. The jumps were not like a tiny object hopping visibly from place to place. They were changes in the atom's internal state, recorded through its light. Still, the effect was unmistakable. A single atom could announce its quantum changes by switching brightness on and off, making the hidden rhythm of energy levels almost tangible. A single atom can emit one photon at a time. Under the right conditions, one atom can be excited and then allowed to release exactly one photon as it returns to a lower energy state. After emitting, it must be excited again before another photon can appear. This makes single atoms valuable sources of individual photons. Such sources are important for quantum communication, quantum optics, and tests of the foundations of light. Unlike a classical lamp, which emits vast numbers of photons in random streams, a controlled atom can produce light in a more countable way. Experiments can measure this through photon anti-bunching, where photons are detected one by one rather than in clumps. The effect reveals the quantum nature of light with great clarity. A single atom becomes a tiny light source governed by strict rules. Each photon is a complete packet of energy, released in response to a specific transition. From one atom, one flash, and one detector comes evidence that light is granular at its core. Atomic physics made modern magnetic resonance imaging possible. Magnetic resonance imaging depends on the behavior of atomic nuclei, especially hydrogen nuclei in the body's water and fat. These nuclei act like tiny magnetic systems. When placed in a strong magnetic field, they align in ways that can be manipulated by radio frequency pulses. After being disturbed, they return toward equilibrium and emit signals. By measuring those signals with carefully controlled magnetic gradients, a scanner reconstructs detailed images of tissues inside the body. The method does not require ionizing radiation, which is one reason it has become so important in medicine. Its origins lie in nuclear magnetic resonance, a discovery rooted in atomic and quantum physics. What makes the technology remarkable is the translation from microscopic spin behavior to large-scale images of anatomy. Tiny nuclei, each responding to fields according to quantum rules, collectively produce signals that reveal organs, injuries, and disease. The human body becomes readable because its atoms answer radio waves. X-ray spectra reveal the inner electrons of atoms. Most visible spectra involve outer electrons, but X-rays can probe much deeper. When an inner electron is removed from an atom, an electron from a higher level can fall into the vacancy and release an X-ray photon. The energy of that photon depends on the element, because inner electron levels are strongly influenced by the nuclear charge. This creates characteristic X-ray lines. Scientists use them to identify elements in rocks, metals, artworks, spacecraft materials, and archaeological objects. The method can be non-destructive, which makes it especially valuable when samples are rare or delicate. X-ray spectra also reveal chemical environments, because nearby atoms can slightly shift the energies involved. The story is compelling because an atom has hidden layers. The outer electrons shape chemistry, but the inner electrons carry signatures closer to the nucleus. By listening to X-rays rather than visible light, scientists read a deeper region of the atom and uncover what material is made of. Synchrotron light lets scientists probe atoms inside complex materials. A synchrotron accelerates charged particles, usually electrons, around a ring at very high speeds. As the particles are bent by magnets, they emit intense beams of light across a wide range of wavelengths, including X-rays. This radiation is far brighter and more controllable than ordinary laboratory sources. Scientists use it to study materials in extraordinary detail. They can determine atomic arrangements in crystals, watch chemical reactions, examine proteins, analyze fossils, and inspect advanced batteries while they operate. The power comes from combining bright beams with techniques such as diffraction, spectroscopy, and imaging. Synchrotron facilities are huge machines, but they are built to answer questions at the scale of atoms. A beam produced by fast electrons in a ring can reveal how atoms are arranged inside a catalyst, or how a drug molecule fits into a protein. It is one of modern science's great instruments, turning accelerated particles into light that can explore the structure of matter. Plasma contains atoms stripped apart into ions and electrons. A plasma forms when enough energy separates electrons from atoms, creating a mixture of charged particles. It is often called the fourth state of matter, distinct from solids, liquids, and gases. Because it contains free charges, plasma responds strongly to electric and magnetic fields. This makes it dynamic, sometimes unstable, and often luminous. Stars are made largely of plasma. Lightning is plasma. Neon signs, fusion experiments, and parts of Earth's upper atmosphere all involve plasma behavior. In this state, atoms are no longer neutral wholes. Their nuclei and electrons move in a charged collective, interacting through fields over long distances. Plasma can conduct electricity, form filaments, produce waves, and generate magnetic effects. It is the most common state of ordinary visible matter in the universe, even though it is less familiar on Earth's surface. Atomic physics helps explain how ionization happens, while plasma physics explores what matter becomes after atoms are pulled apart. The early universe was too hot for atoms to survive. Soon after the Big Bang, matter existed in a blazing state where temperatures were far beyond anything atoms could withstand. Electrons had too much energy to remain bound to nuclei. Any attempt to form a neutral atom would be quickly undone by collisions and radiation. the universe was filled with a charged mixture of particles and light, a plasma that scattered photons constantly. This made the cosmos opaque. It was not dark in the simple sense, but light could not travel freely across long distances. Only later, as expansion cooled everything, could electrons settle into stable atomic states. That change marked a major transition in cosmic history. Before atoms, the universe was a hot sea of charged matter. After atoms formed, light began to move freely, and the path toward stars and galaxies became possible. Atomic physics is therefore not only about laboratories. It describes a turning point in the birth of the visible universe. Recombination allowed electrons and nuclei to form the first atoms. As the universe expanded, it cooled enough for positively charged nuclei to capture electrons. This process is called recombination, though it was really the first widespread combination of electrons with nuclei. Most of the atoms formed were hydrogen, with helium also present. The change did not happen in a single instant everywhere, but across a period when the balance shifted toward neutral matter. Once neutral atoms became common, photons no longer scattered constantly from free electrons. Light could stream through space. This event left behind the radiation we now observe as the cosmic microwave background. Recombination also set the stage for gravity to gather matter into larger structures. Without neutral atoms, the later story of cosmic clouds, stars, and galaxies would have unfolded differently. The term may sound technical, but the meaning is grand. It was the time when the young universe stopped being a charged fog and became transparent enough to reveal its own afterglow. The cosmic microwave background began after atoms made space transparent. The ancient radiation filling the universe today comes from the time when light finally decoupled from matter. Before neutral atoms formed, photons scattered repeatedly from free electrons and could not travel far. Once electrons became bound in atoms, space became transparent to that radiation. The light set free then has been traveling ever since. As the universe expanded, its wavelength stretched until it became microwaves. That faint background now arrives from every direction, carrying a picture of the universe when it was still very young. Tiny variations in its temperature reveal the seeds of later cosmic structure. These variations helped scientists understand the universe's age, contents, and large-scale geometry. The connection to atomic physics is direct. The formation of atoms allowed the oldest light we can observe to begin its journey. When scientists map this radiation, they are looking at the moment when atomic matter changed the visibility of the cosmos. Interstellar clouds contain atoms colder than any earthly winter. Between stars lie vast clouds of gas and dust. Some are warm and active, while others are astonishingly cold. In dense molecular clouds, temperatures can fall a mere little above absolute zero. At such temperatures, atoms and molecules move slowly, and delicate chemistry can occur on dust grains or in the gas itself. These clouds are important because they can collapse under gravity and become birthplaces of stars. Atomic and molecular emissions from them allow astronomers to measure temperature, density, motion, and composition. The cold is far beyond any natural winter on Earth, yet it is not lifeless in a cosmic sense. It is a storage place for future suns and planets. The atoms there may spend long ages drifting in darkness before gravity gathers them into something new. This makes interstellar cold strangely creative. Matter rests at temperatures almost unimaginable to us, while slowly preparing the raw material for future light. Laboratory atoms can simulate physics found inside distant stars. Some stellar conditions are impossible to recreate fully on Earth. The pressure, temperature, and scale of a star are beyond ordinary laboratories. Yet atomic systems can still simulate selected pieces of star physics. Plasmas, ion traps, ultra-cold atoms, and high-intensity lasers allow scientists to study processes that also matter in astrophysical environments. They can measure atomic transition rates, collision behavior, ionization, and radiation interactions. These measurements feed models of stellar atmospheres, white dwarfs, and cosmic plasmas. Sometimes a carefully controlled laboratory system can imitate the mathematics of a much larger system, even when the physical setting is very different. This is one of science's cleverest strategies. Instead of building a star, researchers isolate a rule that stars obey and create an experiment where that rule can be tested. A handful of atoms in a chamber can therefore improve our understanding of objects many light years away. The smallest experiments can speak to the largest fires. Atomic physics turns the smallest structures into the deepest clues. The study of atoms began with a simple question about what matter is made of. It grew into a field that touches almost every scale of reality. Atomic spectra reveal the chemistry of stars. Atomic clocks test time, gravity, and the stability of physical constants. Atomic sensors measure fields and motion with extraordinary precision. Exotic atoms probe antimatter and the limits of theory. Cold atoms make quantum behavior visible in new ways. The reason the field is so powerful is that atoms are both simple enough to study and rich enough to reveal deep laws. They sit between the human world and the subatomic world, translating hidden rules into measurable signals. Every transition, shift, and interaction can become evidence. Atomic physics teaches that nature leaves clues in the smallest details. A line of light, a trapped ion, or a drifting atom can point toward truths about matter, forces, time, and the history of the universe. And so, our journey through atomic physics comes to rest. We began with matter at its smallest familiar scale, where atoms build the solid world while hiding vast spaces within. We followed electrons as they shifted between energy levels, releasing the colors of flames, lamps, auroras, and distant stars. We watched light become a messenger, carrying the fingerprints of elements across laboratories and across space. We stepped into the nucleus, where protons define the elements and neutrons help hold matter together. We saw how quantum rules keep atoms stable, how clocks can count the rhythm of cesium, and how lasers can turn atomic order into a beam of astonishing precision. Then we drifted deeper still, into cold atoms, trapped ions, antimatter, matter waves, atomic sensors, and the first atoms of the early universe. Again and again, the smallest structures became clues to the largest questions. And now, you can let those ideas settle. There is nothing more to hold on to. Let the details soften. Let the strange little world of atoms become calm in your mind. Picture the universe made from patient patterns, each one resting in place, each one following laws older than any star. If you enjoyed this gentle journey, you're warmly invited to like, subscribe, or leave a thought below. It helps others find their way here too, one sleepy soul at a time. And if you happen to still be awake, there should be another quiet exploration waiting on the screen for you. But for now, let your shoulders loosen. Let your breath find its own slow rhythm. Let the day become distant. You have followed matter inward, all the way down to its hidden rules, and now you can drift outward again, back into rest. Sleep well, and good night.